So the next topic is polynomial regression. So far we have covered a linear regression, logistic regression, and polynomial regression, right? So we have tomorrow one class. So I don't want to rush up the portion. So with respect to the CAT, so we have one more topic left over in second module. Is a KNN, right? So the KNN is not for your CAT. So that KNN will be considered for the next exam, CAT 2. Okay. So that KNN I'll teach you after the CAT 1. So that we'll see, no issues. So your portions are for CAT 1, you just concentrate on hypothesis algorithm, finders algorithm, candidate elimination, right? Candidate elimination and your decision tree and random forest, 4 topics in module 1. Module 2, linear regression, logistic regression, and polynomial regression. So in the module 2, we cannot ask any problematic question. So you concentrate on the concepts. So right, so what each parameter, each term, what is the purpose, where do you use, when do you use, when the condition gets failed. So such questions. So the module 2 questions can be answered only by understanding. Keep that in mind. So you have only 4 questions for CAT 1, only 4. First 2. 2 questions will carry 15 marks, 2 questions will carry 10 marks. So 30 plus 20, 50 marks. Okay. Is that clear?
Yes, sir.
Yeah, tomorrow you can consider tomorrow's class, you can use it for practice or study purpose, right? So if you have any doubts, you can ask tomorrow, or else you can go ahead. So let's see. I think tomorrow 5 o'clock, right? So I think tomorrow class you can take it as the preparation class, exam preparation class. So with this today's class, we will wind up the module 1 and 2. So we will meet you all in after CAT 1. Okay. So now we will touch upon the polynomial regression. So the difference between linear, non-linear, linear and logistic and polynomial is linear always go with your, I mean the increasing order in linear in nature. So the logistic regression, so you can generate the data, generate the curve based on sigmoid function, right? So there the prediction is happening like theta is equal to the event happened, probability for event happening divided by probability for not happening. That is nothing but your p by 1 minus p. So that p is nothing but your p of x. So p of x can be identified or generated with the help of a sigmoid curve, right? So that is what this logistic function. The another one is, so suppose if you want to improve, if you want in both linear and logistic, there will be possibility for noise. Noise can be added because if you are not taken the data set, more data set, if you are not consider the more features for training, obviously the overfitting will happen. So what we will do in order to avoid such cases, what we will do, we can add the polynomials, we can add the extra terms into the linear equation, so that you can avoid the such type of errors and you can increase the accuracy. That is the objective of this polynomial regression. So what do you mean by polynomial? Polynomial is generally we used to call as algebraic expression that consists of variables. In all these regressions, we are doing a prediction. What type of prediction? What do you mean by prediction? So what do you need for prediction? For predicting something, you need a variables. What type of variable you need? You need 2 types of variable. One is a dependent variable, another one is an independent variable. So dependent variable is nothing but your x parameter. The independent is nothing but your y parameter here. Suppose this polynomial, I told you, we are adding some extra terms. Instead of x, previously we have only x. Now we are adding x1 squared, x2 squared, or x power 3, x power 4. So here we are introducing the extra terms. We are introducing the many terms. That is what it is meant for polynomial. Nomial meaning terms. Poly means many. So instead of y is equal to mx plus c, we are adding y is equal to mx1 plus mx1 squared plus mx1 cube plus mx1 power 4 plus your c, your constant. So this is what your many terms we are adding. right? So when you keep, so it may be an independent variable. So in such cases, there may be two independent variable. Instead of x1 squared, x1 power cube, x1 power 4, you can add x1, x2, x3, x4. So that depends on the input, whether it is a single variable or multi-variable, multi-class classification or regression. So this is the key objective of this polynomial regression. So when you say regression is mainly, it's a predictive modeling technique, right? We used to call prediction. We are doing a prediction. We have come across many examples with respect to the regression. So I don't want to go much into that. So what is a polynomial regression? Polynomial regression is nothing but a relationship between independent and dependent variable as nth degree polynomial. Okay. As the nth degree polynomial, it will go up to nth degrees. Suppose if you place the value for x1, x2, you will get some kind of accuracy. What you will get then the independent variable of accuracy of y. So this polynomial regression we used to call, we are finding the best fit line by using the linear equation. When you add linear equation with the polynomial regression polynomials, it will become a polynomial regression. That's all. The logic is very simple. Linear plus your polynomial degrees is nothing but a polynomial regression. So where does this linear regression fails? Suppose if you are not consider the more more data for your training. Suppose assume your data set has 10 rows. Out of 10 rows, if you want to do training, if you want to train your data, if you want to train your model, what you will do? Generally, we will take 1 by 2. Then out of 10 rows, we will take 5 rows. You are not doing any pre-processing or cleaning or missing values. You directly will apply with your directly used for training. So out of 5, there may be a positive hypothesis 3 or negative hypothesis 2, 3:2. So in such cases, if you train your model, what you will get? You will get 60%, 70%, 30%. So whenever you use more data set, more training examples for your training, obviously your accuracy will get improved so that you can avoid your overfitting issues. So or else it will be, you will either end up with your either overfitting or underfitting. Out of 10, if you take one variable sample or two variable sample, obviously we can say it's underutilization or underfit. None of the parameter, none of the points will fit in that linear regression line. So you need to keep the line such a way your points will be fitted. So we need to find the best fit of the line in that regression. That is what this linear regression and polynomial. Suppose if the values are keep on adding, see if the values are static, also it is increasing in nature, obviously we can go with linear model. Suppose you take any other restaurant system, every day, every time there will be different dishes, different menu, different types of visitors, different age group people, there are different people will visit. So this restaurant profit is depends on the different parameters, age, visitors and location, menu, again the chart, everything, right? So such cases you cannot use your linear regression, so it will go. Best example, you take your COVID system, daily cases. So the cases are increasing daily. One day it will go down, one day it will increase. So whatever the graph you see by the government of India, so completely it is a polynomial regression. So graph will go in all direction, zigzag, all anything, right? So such examples are your polynomial regression. Sometimes it will fit yesterday point and today's count, affected count may match, so it will fit in that line. So that is your polynomial regression. So right, this is your left x1 is your example, your linear regression. The right one is your polynomial regression. Generally what we will do, we will take this blue color ones are your training set and the red color one here test set. Training set is always you need to take more than the what do you call, at least you're more than the half of the data set, right? So if you have 1300 data set, at least you take say 800 or 900. You should not go lesser than the average, so that you should not do. So that this blue line is a regression line, so here green line is a regression line, so that the point will come and fit in the run line. So if you do more training, right? So this generally what will happen, so generally it is very difficult to fit the linear regression line in the above graph with low value of error. So logic behind this, if you are not using proper observation, proper data sets for training, obviously you will end up with your low error meaning low bias meaning your overfitting, right? So hence we need to try to use the polynomial regression line to fit the polynomial lines so that we can achieve the minimum error or minimum cost function. Generally, this you can say y is equal to theta plus theta 1x. Generally, what we will do here, how we will write, generally it is y is equal to, so we will write as our school practice, we will write mx plus c. So here the m is nothing but your theta 1. So y is nothing but y. Again, this constant is nothing but theta 0. So now this will go, now this is x to the power 1. So when you take this alone, this is your linear equation. When you take whole set, we can say it is the polynomial regression. So the degrees are followed, degree 1, degree 2, degree 3, degree 4. So that is how this concept is all about. So the general equation of polynomial regression, this line linear equation plus your residual value error, that is nothing but your polynomial regression. So this is your polynomial function instead of your straight line. So this will go like this. See the curve. So this is fitting best fit, best fit, best fit, best fit, best fit, and best fit. So such kind of things are polynomial regression lines, right? So here what we will do, so when we will get the curvilinear relationship. Generally here we will get the curve when you work with multiple independent variable and dependent variable, we will use your curvilinear relationship, curves generally. So there are three types of polynomial regression. When you say degree is your 1, we call linear, degree is 2, we can call quadratic, degree is 3, we used to call a cubic. So it will goes on like this 4 and 5, 6, so right. So if it is a linear polynomial, then we can say example x plus 8, so x to the power 1, right, that is your linear. Suppose your x to the power 2, then you can say quadratic polynomial. If the degree is 3, then you can say it is cubic polynomial. So this is your types of polynomial regression, right? So the corresponding equation is given. b0 plus b1 into x1, same. So this is multiple linear regression. Linear regression, multi-linear regression is here multiple variables will be there, x1, x2, but the equation wise same. But polynomial meaning we are adding extra terms, that is in the degrees 1, 2, 3. So these degrees are added. So at the end, so that is what polynomial linear regression. So overfitting, underfitting, I told you overfitting is because of your less trained data. So what you need to do, you need to increase the number of training samples. So if you have almost 2000 rows, at least you take 1200 rows for your training, so that the algorithm does not learn the system noise and become more generalized. So or else the noises will be introduced or values maybe might have missed. So such things are avoided when you use more training samples. So what is the bias and variance? Bias meaning, as you know, there is error. So bias is nothing but a mistake or an error. So it is caused by the model's simple assumptions in fitting the data is referred to as a bias. So low bias and high variance is called overfitting. High bias with low variance is called underfitting. So bias meaning error, variance meaning changes or a difference, right? So with the actual and the predicted, that is what this overfitting and underfitting. Trade-off meaning, so trade-off, so there should be a what do you call? There should be a difference. Complex models, so that whenever the model complexity grows, the bias reduces while the variance increases, and vice versa. Sometimes bias increases, variance will be decreases. So such things we used to call minimal variance and bias, right? So suppose this having a both category, minimum variance, minimum bias is very difficult. It is impossible. So if you try such cases, we used to call the trade-off will happen. So trade-off must be made in order to build a strong model that performance well both in trained data and seen data. So if you want to achieve minimal variance and minimal bias, then obviously the trade-off should be made so that you can avoid such things. You can see here the overfitting and the underfitting example. So it's a overfitting. All the points are fitted on this curve, right? Maybe this might be included your noises and errors and the differences, etc. So here underfitting meaning is totally away from this regression line. So good fitting meaning is the major points are fitted, the major samples are fitted, other samples are somewhere. So such things we used to call your good fit. Trade-off is a tension between the error introduced by the bias and the variance. So loss and cost function. Loss is generally refers to a single training example. So then whereas your cost function we used to used for a complete training set. So when I say cost function, so you should calculate for the overall data set. So meaning the average of the sample errors in the data. Whereas loss function is the error for the individual data points. What is the error in individual row, individual data sets? That is your loss, cost meaning the overall. So finally the cost function is calculated 1 by n summation of 1 to n predicted value comma expected value squared. So now there is a sample problem is taken. So now we have two independent variable. One is a position, another one is the level. Job position, another one is a level. There is an independent variable called salary. So this is what our problem statement. So in this problem, we have to train polynomial regression model with this data to understand the correlation between the level and salary of the employee data in the company and be able to predict the salary for the new employees based on this data. So understand you have a two variable x1 and x2. Assume x1 is your position. So from this you can understand this is a multivariable statement problem. X1, x2, then salary is your y. So this is what the given. So now we need to predict the salary for the new employees. Okay. So as usual, what we will do in Colab or Jupyter book. So simply we will import the data, library, NumPy, Matplotlib and Pandas. Then after importing, you will import the data set. Just I am importing the data set is position is equal to salaries. Then I am avoiding the last column. So same is a -1. So that's I am avoiding -1 last column values. Then y is nothing but same. I am avoiding last column values. So I am printing the first 5 rows in the data set, head of 5. So now I need to use I need to remap with the polynomial regression with the linear, right? So for that, instead of x, I am using x poly. Instead of y, I am using as like y only. So now the same pre-processing import polynomial feature, because as I told you, polynomial is nothing but a linear regression with the degree. So linear regression to be imported. So the features are I am using in degree of 4. So then I am fitting into the best line, I mean best of the line, fit line. So polynomial underscore regression dot fit of transform. Then I am calling the linear regression. Then I am using the x poly along predicted variable comma actual variable. That is what this variable is nothing but. So predicting the result, as you know, so y prediction is nothing but our predicted value. So that is linear regression dot predict of x poly. Based on x poly, I am predicting that is your y poly value. So finally, these values are kept it under the variable called real values and the predicted values. So we can see that the model has done a great job in fitting the data and predicting the salary of the employee based on the position levels. See here there are different positions are available, real values based on that the value are predicted. So now we want to visualize the data. Same what we will do, we will visualize through plot. So title, xlab and ylab and show. So the logic behind is the predict of yes plt dot plot of x grid comma linear regression dot predict of poly underscore regression pit transform of x grid. So here whatever given here. So this x poly comma y. So same thing should be given here. X poly. Where is x poly? Fit of transform is a x grid. So x grid is nothing but here numpy dot arrange of minimum x comma minimum x, sorry, maximum x comma 0 into 1. Then x grid is equal to x grid dot reshape of length of the x grid comma 1. So we are considering only true values. So then scatter plot of color is equal to red. Scatter plot of the predicted value is green. So this is y is your actual value. This is your predicted value. Red and green, meaning 0 and 1, right? So now this will be drawn like this. So the real values are plotted in red color. Predicted values are plotted in green color. See here, all the values are fitted almost. So this is what your polynomial regression. So this curve like this, right? So this is the some other curves, degree 1 curve. So degree 1 is nothing but your linear, right? Linear regression is equal to polynomial regression. Then degree 2 is the polynomial equation, degree 4 polynomial equation. So here you will get one curve. See the point. So this is your 1, here a curve point 2. This is your 3, this is your 4. So 4 minus 1 is your degree. This is your 3, degree is 3. This is how you may ask, how do you say degree 3, sir? So here it is 2 starting point and ending point. So this is we used to call order. Order minus 1 is equal to your degree. This is what this order minus 1. So minus 1 is nothing but your degree. What is the order? Order nothing but control points. Control points is your order. Okay. If you studied computer graphics, you'll come to know. So now these type of curves we used to call Bezier curve and splines generally. So this is your here one curve. See, wherever there is a turning point, the curve will start from here. Again, it is here. There is a bend. So here there is one control point, something like this. See here. So here it is starting. Here one starting. Here one cut. Again here one cut. Here one cut. So 1, 2, 3, 4, 5. So 5 minus 1 is your 4. So the degree is 4. So this is what your control points. Even if you open what do you call Word. See, I'll show you the Word document. I'll take some blank document. So if I will draw something like insert shape. Where is shape? See here. I am drawing. I am keeping this shape, right? This is 4. So if I say what a control point of this, so you can see the edit point. See here, you can see the control points. How many control points? 1, 2, 3, 4. 4 minus 1, 3. So this order of this equation is the 3. Similarly, for everything there is a control point. How this is drawn? So it will straightly, it is drawn, illustrated. From here there is another turn. So control point from here there is some 30-degree angle. It was drawn. Right shape, something like that. Same here. See here the curve I am keeping here like this. This is my curve. Now see the curve eddy control points are, see here, 1, 2, 3, 4, 5. 5 minus 1 is 4. So this is my control point. So similarly, this is how your even I'll keep this. You can easily guess. So that is your control points. So order is equal to degree is equal to order minus 1. Order minus 1. Order is nothing but number of control points. This may be useful when you prepare. So this is here something like this. Okay. Is it okay? So now there is another representation. Suppose see here x. So I have x value 1, 2, 3, 4. This is linear in nature. This is gradually increasing. So I definitely I know I will get a straight line. So now these values are scaled up. So that is up to the degree n. So see x squared, x cube, x power 4 up to xn where it is scaled, right? So now assume there is a degree set, data set degree is 4. Then if it is x squared now 1, x squared cube 1, x to the power squared now 4, 8, it is 16, 32, it will go like this. Now I have equation, assume there is a equation. So polynomial regression equation with the multivariable. So x1, x1, x2. So now b0 plus b1 x1 b2 x squared. So this is single variable. This is a polynomial. So only I have only one variable x1 only, not x2. So now this is your independent variable x1 are independent variable, whereas y is your dependent. This depend because this y's results is dependent on this entire equation, right? So now if you have only one independent variable, then you will get curve like this. See here. So you will get curve like this. So this is what the curve. So here only one control point. Suppose if you have multiple, more than one independent variable, then how will you do it? There will be different wherever you pull. So that will be, it will come like example. What do you call? I think Bezier curves. I think I have some kind of thing. See here. So these are the Bezier curves. We can say it is a 3 control points. In between there is a point. So this is the another curve. So we used to call quadratic curve. So quad means 4. So here 3 minus 1 is 2. Cubic curve. So 4 minus 1 is 2. See here, when you say the control point, here there is one control, here there is one control. P0, P1, there is a control. When you pull here and there, the curve will change. Curve shape will change. That is what we are saying. It is the cubic quadratic. So, right, I'll have some curve designs. See here, I am just showing the curves. See this curve, you can move these control points using mouse. See here, I have the control point for this one. So we may say this is the only control point. But see here, if I change this control point, the entire curve shape will change. See here. So if it is Z type curve, then I need to keep this dot here because 0 to 1 range. So this is S type curve. If I bring this proper S type shape curve, I will get it. So meaning I used to say here there will be a total 4 control points. How do we say this one is the first control point, this bend is another control, the third is another control. So how this is happening, because this curve shape is changed. What do you call? See now. This curve shape, this bend is the bend is controlled based on this control point. Same, this bend is controlled based on this point, control point number 2. This is what the control points, right? Control points, so that you can easily understand. See, so if I want to change this bend, so what I will do, I will move this second control point. See, the curve is completely changing. If I keep this line and this y's intercept, then this will be a curve, parabolic curve. So now I am bringing this 4 to down. You can say this half parabolic curve, C type curve. So suppose I am bringing this third control point here, there is a curve shape will change. See here. So this bend is based on this points. So this is where, see the car, the alphabet A, the jug, everywhere there is a control points. This is the polynomial degree. This is the equations, right? So see the curve is changed. So when I play the time series 1 to 5, see the linear regression, this line. So the curve, the regression line. So the curve is generated based on this regression line. This is what we used to call, right? So these type of curves we used to call your polynomial regression. So that is what I am trying to explain. So if there is only one variable, then you will get a curve like this. If you have more independent variable, then you will get curve like this. This type of graphs you will get, right? So that depends on the data set. What are the advantages of your polynomial regression? Polynomial regression always gives the best approximation relationship between dependent and independent. Also, it will give you broad range of functions. Also, the polynomial basically fits with a wide range of curvature. Also, this what do you call this is accommodate the different variables. So it will avoid the your error rate, right? So disadvantages are generally the presence of one or two outliers in the data. It can seriously affect the results of the nonlinear analysis. So we need to try make sure that there should not be any outlier or missing values in the data set, or else it will affect the entire linear analysis, right? So this is how your polynomial regression. Next one is a gradient descendant. So what do you mean by this gradient descendant? Gradient descendant is one of the technique which is used to avoid your errors. How do you optimize the techniques? How do you optimize the algorithm? So one of the most frequently used technique is your gradient descendant. Gradient descendant is the one of the machine learning technique which is used to minimize the errors. That is what your this equation is all about, right? So this error rate is used to call this phi. Y is equal to b0 beta 0 plus beta 1 into x. This is what generally we used to call your linear equation, this alone. So when you say polynomial, your polynomial regression, then your obviously your this is a residual parameter will be added. So this I say phi I is nothing but a random error term whose roles is to add bias. Whenever there is a error in your data set, then meaning that this term will be added here. That is what this term. How do you minimize this random error component? That is what your gradient descendant technique is all about. So how do you do this? So generally, how do you reduce this error value? Generally, we introducing the gradient descendant. So how to minimize that cost of that gradient descendant? Meaning by simply you need to retune that parameter. So that depends on this theta, h and y, this theta, j and h. So j is nothing but your cost function. So cost function meaning error function. What is the error rate in that involved in that function, right? So then y is nothing but your predicted value hypothesis function. H theta is nothing but your hypothesis function, y prediction. So if you manage by retuning this theta value, you can reduce the errors. That is what this gradient descent is all about. Suppose if you have only one variable in that Polynomial regression, you will get a single type of curve where whenever there are more variables are involved, theta 1 and theta 2, obviously you will get a curve like this, right? So this depends on learning rate. So machine learning rate. So machine learning rate is depends on how large of a step we can take to the each iteration. See here, 0.9, 0.8, 0.6, 0.6. It is the step size is very minimal. We are not taken any too large step. So if we taken, again it will go to the last. So what we will do, we will take the minimum steps, so that we can we can arrive the with less error. That is what this gradient descent is all about. So we will see gradient descent in detail in later slides. So for example, this is one of the prediction, second order prediction. See b0 plus b1 x1, b2 x1, b3 x2, b4 x2. So x1 and x2 is used. There are two independent variable is used, right? So now I am applying, so I am taking some random equation, whereas I am applying x1 is equal to 2, x2 is equal to 4. When you apply this value to this equation, you will get 90.4. So a regression value. So 95.4 is your predicted value. You may get a question in exams. Make sure such kind of equation might be given. They will ask you to identify whether it is a single equation or double equation. So you need to answer it. So what is the predicted value by the polynomial regression, right? So there won't, so nothing like that. Yeah, that's all. So this is how this gradient descendant and the polynomial regression is all about. So as a summary, we have seen the steps involved with the data processing. What is a linear model, polynomial regression, overfitting, and gradient descendant. Finally, you need to fine tune the parameters of the data, right? So this is what here what you have learned so far. That is, I just kept a summary slide. So linear regression, so parameters, loss and function, problem analysis, gradient descent, and prediction. So this is what we did. I'll show you the demo of polynomial regression. So that you'll understand. Yeah, got it. So this is your library. This is your, I will run one by one so that you will understand. I am just running the library. I am just uploading the data set. See here the regression line was generated. So how many lines? Red color lines are your testing, green color as your polynomial regression. So fitting. So this is how your, after this you can draw the confusion matrix, you can calculate the accuracy, precision, recall, everything. So but the graph generation, so this is what the graph generation is all about, right? So I'll upload this data set, or else there are many examples are there in the internet. So even repositories you can use it. Okay. So this is how your polynomial regression is all about. Okay. So if you have any other doubts, you can ask. So far we have covered three types of regressions. So next class after cat 1 I will teach you KNN. Okay. For exam there is no KNN, so only these three topics.
Excuse me, sir.
Yeah.
Sir, could you kindly share the PPTs regarding the regression?
Yeah. Oh, I forgot. Today I'll upload all the. I mean, module 1 is over. No, module 1 PPT.
Yeah, yes, sir. Module 1 is uploaded.
Let me check 1 second. Reconfirm. So you can refer module 1 full PPT. Similarly, I'll upload module 2 also. I'll convert this linear logistic polynomial descendant. I convert all these PPTs. Karna, can you check then check now? Kana, can you check the PPT now?
Yes, sir. It has been uploaded, sir.
Okay.
Thank you,
Four
sir.
PPTs four PDF I uploaded. Just refer it. First module PPT, it is mentioned like module 1 full PPT. Okay. Okay. So thank you all. So all the best. Do well your CAT exams. We will meet later. Okay. Tomorrow no class. You can prepare for your CAT exams. Okay. Thank you all. You can leave. Yeah.
Thank you, sir.
Thank you.